Which of the following provides evidence for the particle model of electromagnetic radiation? Okay, so let's go through each of these options. We'll start with diffraction. So if you think about sound passing through a doorway, the reason that you can hear someone talking in a different room, let's say, even though you can't see them, is because of diffraction, at least to some degree. There will be some reflection as well, but diffraction is a big part of that. It's the same kind of thing as when you pass light through a diffraction grating, or if you pass light through a double slit apparatus. The light spreads out when it goes through each of these slits. So if these are your wavefronts, if this is your slit, the light will diffract, and that is a wave property. Interference is also a wave property. So if two waves meet at a point, so here's one wave, here's another wave, and let's say they're meeting at a point, the resultant displacement will be the sum of the individual displacements of those two waves, which is the principle of superposition. So basically, these two waves meet at a point, and they have a resultant displacement of what we see over here. That is also a wave phenomena. If you have two particles meeting at a point, like if you literally think of like two marbles or something trying to meet at a point, they will just bounce off each other. They wouldn't interfere, at least not in this sense of the word. It is also not polarization. Polarization is a wave property, so only transverse waves can be polarized, transverse waves being those that have an oscillation which is perpendicular to the direction of energy transfer, which would be in this case, in my example, towards the right. So the wave oscillates this way, the wave travels this way, transfers energy this way, and that's perpendicular to the direction of oscillation, which is vertical. And polarization is when all of the waves oscillate in the same direction. So to have polarization, you must have transverse waves. Particles are not transverse waves, and therefore it is not evidence for the particle model of EM radiation. So it must therefore be visible line spectra. So why is it D? So let's think about emission spectra. So if we have a few energy levels of an atom, so this is 0, 1, 2, emission spectra are created when you have an atom de-exciting from one level to another, emitting a photon, and the photon has an energy equal to the difference between those two energy levels. So electron falls from here to here, releases a photon of energy E. The energy of E is equal to the energy of level 2 minus the energy of level 1. And what we see from the different de-excitations that we can possibly have, in this case there's 3, we have 3 possible de-excitations, is we will see 3 frequencies of light being emitted from that atom as it de-excites. In the particle model, the energy of a single photon is given by hf, so the fact that we see only 3 frequencies suggests that this equation here is true, and that supports the particle model of EM radiation. Again, the particle model of EM radiation, part of that model involves light traveling as photons, and the energy of those photons being hf. So if we know when we have de-excitations from this particular type of atom that we will see 3 photon energies, then if the particle model is true, we will see 3 frequencies, which we do. 3 discrete frequencies, and therefore visible line spectra is evidence for the particle model.